stuff with Logisim, okay, and I thought I'd point this out in case you guys wanted to play with it on your own machines. Um, did I put it in here? Yes, okay. You can download this for your own machine if you just look for Logisim Evolution and then at the top hit this GitHub page. Um, and then if you scroll down, you'll see download and you want platform specific packages. Um, and that'll take you to a page where you can download either the Windows installer, which is the .msi, or the Mac OS disk image, which is the DMG. And does anybody have like a Chromebook or something that's sort of different from from either Mac or Windows? No? Okay. Is anybody running Linux on their machine? Also no. Okay, big shock. Okay, anyway, so point being they're right there, so you can download and play with them. So since I'm on the Raspberry Pi, I have to use the Java version. Okay, and that'll take a second and fire up. Um, okay, so last time we built a half adder circuit. So let's just remind ourselves how we did that. Okay, if I have 2 bits, and let me blow this up so it's a little easier to see. If I have 2 bits, and I'll call this one NA and another one that's input B. Okay, oops. And I want to add these things, then we need to generate 2 outputs from the addition, right? We need to generate a sum and we need to generate a carry. Now, either or both of those bits could be 0, but we still have to compute them. So we'll call this sum and this one the carry. Okay. Oh, and actually, you know what? Let me copy these things real quick and make a new sub-circuit. Okay. So over here I can make many different sub-circuits, and I'm going to put them there and then delete the original stuff, oops, that we had, and I'll show you why in a minute. Okay, so there we go. Okay, so there was what we we're starting with, and let me just scoot these over to the right, and let's get the circuitry in between. Okay, so we needed 2 Boolean operations here, right? Under what conditions did we get a sum? Which circuit or which component did that for us? The XOR gate, right? So that was this one here. Okay, and so the XOR gate gave us the sum because under what conditions do we get a 1 for the sum? If one of the inputs is a 1 and the other is a 0. If both of them are a 1, what do we get? A 0, but then we get a carry. Okay, so what Boolean gate will generate the carry? The AND gate, right? So so we put that here, and so we've got, okay, and so I need to take NA, and then of course this one I'll just wire around here. Okay, so the wires that cross each other, if it's not clear, they don't actually touch unless there's that dot, right? So so that's how you can tell whether or not it's supposed to be connected or not when they cross. Okay, so does this rings a bell from last time? Ding ding. Okay. Um, so if I hit the little finger tool here, then I can change what the bits are of my inputs and see that, of course, it's functioning correctly. Okay. And so, yay, that's great. Okay. Now, the reason that I put this in a subcircuit is because then what I can do is sort of zoom out a layer and think of the addition or the half adder that we just built as itself a singular little unit, a magic box. Okay, now what's inside that magic box? Well, an AND gate and an XOR gate that were wired up as we just made them. But if we sort of zoom out, we don't really care now at this moment what was inside that. And I can take this thing that has two inputs and two outputs, and if I build other circuits to go with it, then I can start to string these sorts of computational units together to build a bigger object. Okay, does that kind of make sense? Okay, so the next thing we need to build is a full adder, okay, and that will end up taking 5 gates, as we'll see in a moment. Um, so why do we need to have what's the difference between a half adder and a full adder? Uh, what do we need to do if we're adding the next bit position of, say, an 8-bit number? Well, the sum of the next number might depend on the carry of the previous uh, bit position, right? So the circuits for the full adder really have 3 inputs. The 2 bits that we're adding, along with possibly the carry bit from the previous position. Okay, does that make sense? All right, so we got to figure out how to do that. Okay, and so that circuit's a little bit more complicated, and it's called a full adder, which I'll just call adder here. Well, I'll just say full adder. Right? Okay, so the full adder is going to start looking similar to this. So let me just, for sake of speed, go ahead and copy at least some of this, and then I'll kind of delete a few things. Oops. Ah, damn it. Okay, I should have just done it from scratch. Okay, so we've got 2 inputs, but what also do we need to worry about in this case? Yeah, okay, so let me sort of scooch this and shrink this a little bit. So I might have had a carry from the previous bit position, and so I'm going to think of this here as I've got 3 inputs, okay? The carry and the 2 bits. And then the output that I need, um, I could have a carry, uh, and of course I've got the sum, okay? All right, so similar at least start, but the circuitry here is going to be a little bit more complicated. Um, and so for sake of time, let me just cheat and um, just throw this in here. Okay, so what did we have to generate the sum before? We had an XOR gate, right? Okay, so if I XOR the 2 inputs, this will give me the sum, okay? Um, but I could also, what would happen if the sum is a 1, or sorry, yeah, what would happen if the sum is a 1 and there was also a carry from the previous position? I would have to add that also, okay? And so in order to do that, I'll just throw another XOR gate here that will take the results of the regular sum and then also include whether or not there was a carry, okay, like so. Okay, so let's think about this and make sure that that makes sense. Let me scoot this one down so it'll be nice and tidy here. Okay, so let's think about that. Does that make sense, right? Under what conditions do you get a 0 or a 1 for output if you're adding three things together? Well, if there's three things, how many possible combinations do we have to check? Nope, not quite. 8. You were. But how did I get 8? 2 times 2 times 2, right? Because how many options are there for each of the three bits for the input A, input B, and the carry? They could each be either a 0 or 1, and they're all independent of each other, so you multiply to get the number. All right, so there would be 8 possible combinations to check here, all right, and we could run through checking all of them, right, but we don't have to if we just use our damn heads, right, because we already know that the sum of 2 bits we handle with an XOR gate, and you get a 1 precisely when one of the inputs is a 1 and the other is a 0. Okay, so this XOR gate is the same basically role as the XOR gate that we had in the half adder, right? But now we have the possibility that there's also a carry, and so we need to throw him into the mix. And how do we add basically? Well, it's XOR. Okay. And like I said, you could check all 8 combinations, but this will do it. Okay, now we also need to do the carry stuff, okay? And the carry things is going to be a little bit more complicated. We'll need 3 gates to handle that, okay? Okay, how did we check if there was a carry before? We had an AND gate. All right, let me put this one here. And we had input B came into it and input A came into it. Okay, so this, if that AND gate is a 1, meant that there was a carry generated by input A and input B. Okay, how else could a carry be generated? Almost. If there was a carry coming in and the result of this addition is a 1, right? So this addition here, then I have a 1 and a carry, okay, which should generate another carry. Okay, so I just said the word and, okay, so that means that I need to take the input carry and the result of the addition of the two things and do that. Okay, and let me scooch this one. Okay, so either of those two ways were ways to generate a carry, right? And I need to take 2 possibilities and turn them into one output, and either one of them could be true, maybe both. So what gate do I need to throw, right? Yeah, what do you think? An OR gate, right? Because it could be either one of those possibilities, okay? Including both possibilities. So that's why I put an OR gate here and not an XOR gate, because it's okay for both things to be possible. Okay, and that gets us our full adder. Okay, so notice that what's in here, okay, this XOR gate and this bottom AND gate were kind of playing the exact same role that they were in the half adder. The other XOR gate, the other AND gate, and the OR gate were the new things, right, to deal with the fact that, of course, we had, more complicated logic here. Okay, so that gives us a full adder. All right, let's pick a number and check whether or not it works. Okay. Now, first off, we actually have a number picked right here. If everything is 0, shouldn't we get zeros for our outputs? Right. Okay. So we're good there, right? But let's say that I had 1 and 1, and there was a 1 carried from the previous position. Okay. What should my sum be, and what should my carry be in this case? 1 and carry 1, right? Yeah, sum 1, carry 1. All right, so if I make all three of these things 1, do I get sum 1, carry 1? Yes, okay. What about if I have 2 1s but no carry from the previous position? I get sum 0, carry 1. Does that make sense? What about if I have a 1 but no carry? I get sum 1. What about if I have a 1, 0 and a carry? I get 0, carry 1. Does this look like it's jiving? Okay, well, great. So there we go. All right, so any questions about this particular circuit? Right, a little bit more complicated, but you see how we can kind of piece it together? Not too horrible? We? No? We? Okay. All right, so now that we have a so I'm going to make one version, another version of this, okay? So let me just select everything, and I'm going to call this a last adder. This is not a standard name, it's just one I made up, okay? And then I'm going to start deleting some stuff. Okay, so what I've done here is deleted basically everything that did the carry logic from before, okay? And the reason I've done that is because, well, if we add two 8-bit numbers, as we've done, we would use a half adder on the far right bit. The next 6 bits, we would use a full adder, but then the far left bit, do we carry from the 8th bit to something? No, that carry just disappears, okay? And so do I need any of the stuff down below that generated the carry logic? No, okay? So what I'm going to think of is if I have two 8-bit numbers, right? So I have, you know, something, and let me just make up some numbers. Doesn't really matter here, right? This bit position, what circuit do I need? The half adder, okay? All right, so this one, I need a half adder. For these 6, what am I going to use? A full adder. And then this last bit position on our Brookshire architecture, and also when we did all this stuff by hand, what happened if there was a final carry? We just threw it away, right? And so this last bit position will do what I called a last adder, okay? Now I should say that in a real architecture, that final carry could get stored someplace if you wanted to, but it would get stored into a special thing called a flag register that basically just was sort of like a scratch paper that kept, you know, hey, was the result of the last computation 0, yes or no? Did the last computation generate a carry, yes or no? Right, so some sort of those sorts of things. But the Brookshire architecture doesn't have that, so we don't have to worry about it. All right, and which is why we can simplify this and do a last adder. Okay, so now that I have these three pieces, if I go to my addition circuit, I'm going to take a half adder, okay, and then how many full adders do I need? I need 6 of them. Okay, so while I'm copying and pasting this, I wrote two numbers up on the board just kind of randomly. By hand, do the addition real quick. And then we'll put those into our simulation here and make sure that we actually get the correct answer. Okay, so just add them by hand real quick. I'm going to zoom this out for right this instant, just so I can get everything in place. All right, 1, 2, 3, 4, 5, 6. And then my last adder. Oops. Okay. All right, now let me scoochie these guys. Oops, damn it. Okay, so I need to have two inputs, but how many bits are these inputs going to be? They're going to be 8-bit inputs, right? Because I want to add two 8-bit numbers. So I can change these to be 8-bit inputs. And I'll call this one NA. Okay, so that makes sense, right? Okay, now what do I need to do to sort of connect all of this? So let me kind of zoom in for sake of clarity. Right, so I need to start connecting these two input numbers into all of my addition units. So what do I have to connect from input A into this half adder? Okay, I can't just connect the whole damn thing because this is an 8-bit object, and what are the input A and B here? How many bits were those? Single bits. Well, 8 is not equal to 1 the last time I checked. So I need to do something. Which bit do I want from here to go into into my half adder? Yeah, the least significant bit, the far right one. Okay, and what would go into the second one? The full adder, the first full adder, the second bit, and then this one, and etc. Okay, and ditto with input B. So what I need to do is take this 8-bit bundle and split it up into 8 individual bits. Make sense? Okay, so you can think about this. I mean, this is actually somewhat accurate of a way of thinking about it, is that this wire is really a bundle of 8 little wires. Well, couldn't I open up that bundle and split out each individual one? Right? Yeah, okay. And so the way that we do that in this program anyway is with a thing called a splitter. Okay, and I have how many bits? Oops, that was not what I meant to put. I have 8 bits, and I wanted to fan out in 8 pieces. Oops. Okay, like so. So let me scoochie him down a little bit. And oops, let me connect this. Okay, so what do I need to connect from my fan out here to here? Which one? The 0th bit needs to connect to here. The first bit needs to connect to here. The second bit, you guys kind of probably see the pattern at this point. Okay, and so on, right? I just got more clicking to do. Yeah? Okay, so I would need to go through and do all of that, right? And ditto for the second number. Now, you see on my little splitter here that we've got the numbers 0 through 7. those indicate the bit positions. Bit 0 is the far right bit, the least significant bit, and bit 7 is the far left bit. And the convention, as we've seen plenty, is you start counting with 0, not with 1. So that's why it's 0 through 7 and not 1 through 8. Okay, but is that okay? Right, and obviously the order of these things matters because if I have them out of order, then it's going to be all jacked up. Okay, does that make sense? Okay, so to finish wiring this, I've got to do the exact same thing with um, the rest of the input A bits, and I need to do the same deal with input B. Okay, so it's going to kind of turn into a rat's nest here, but that's the idea. But then there's one other thing that I need to do, which is where do the carries come from? Yeah, exactly, from the previous addition unit. So let me kind of scooch over to the right here, right? So where does the input carry for the first, for this come from? He comes from over here. Okay, and then similarly for all of the other ones, their carries come in from the previous addition unit. Okay, and so I would just need to kind of keep snaking those things around. Okay, but again, sort of same deal, just more clicky clicky. Okay, okay, so then let's imagine that I've connected everything that I need to. Okay, then the last thing is I need to put the answer back together, right? Each of these 8 addition units deals with one of the bits of the answer. And of course, the answer is a 8-bit thing. So I've got 8 individual wires, and I want to bundle them back up into an 8-bit sort of collective. Yeah? All right, so I used a splitter to split a bundle into its 8 individual components. Could I do sort of the opposite process and bundle them all back together? Yeah, of course. And actually, I'm going to use the splitter again for this. I'll just sort of flip it around. Okay, so if I come over to my output side, okay, then I'm going to do a couple of things. I'm going to make it face the other direction, just for convenience. Okay, and then I can take the 8 individual sums and bundle them back up. So I can take this is the 0th bit, and then I've got the first bit and the second bit, okay, and so on. And then I can call this thing, the output is an 8-bit object, and I'll call it the sum. That was not what I meant to do. This one. Okay, and so you see how it says U 000? Because I've only got 3 connected. So what do you think the U stands for? Undefined. Yeah, and it's only because I don't have them connected yet. Okay. But I mean, you guys get the idea, right? I just need to keep, you know, clicky clicky until I've got everything put together. Okay, so does that kind of make sense? All right, now that I've built this, well, and let's just pretend for the sake of time that I've finished it. All right, let me save this so that I'm okay. Well, I can think of, right, zooming out even one more layer and saying, okay, I took a bunch of gates to build full adders, half adders, and last adders, and then I zoomed out and thought of those as just magic boxes. And then I put these 8 magic boxes together to produce another even more grandiose magic box, which I'll call an addition unit. Okay, and this is sort of how we kind of think about, like, architecturally putting together all the pieces that would actually make a processor work. A processor needs to have an addition unit. Well, we basically just built it, right? And then what else would we need for say the Brookshire architecture? What other components might we need here? Well, what other operations can that thing do? There's 12 of them. What are they? Any? Okay, jump, that one's complicated, as we've seen. Store, load, move, etc. Okay, but we also have, what were the other logical operations? We could do addition, but we could also do the logical operations. So yeah, we could do bitwise and, we could do bitwise or, and we could do bitwise XOR. Okay, and then as we've seen, by combining those in clever ways, we can actually do bitwise negation. How did we flip all the bits? What was the trick? Yeah, XOR just to flip the bits. Okay, so the negation, yeah, we need to add 1, but when the flipping the bits part we do with XOR. Okay, but using XOR is only 1/2 of the Texas two-step, right? What else do you need besides the logical operation? You need a cleverly selected bit pattern. Okay, so XORing the number against what to flip all the bits? All ones, okay, or FF and hex, right? So that's how we flipped bits. Well, that's bitwise not. That's the ones complement. If we then add 1, we get the twos complement, which is how we did negation. Okay, so if I wanted to build a unit, okay, that handled all arithmetical and all logical operations, what else do I need to build here? I need to build the AND unit. I need to build the OR unit. I need to build the XOR unit. And I need to build the rotate unit. Okay. I would also need to build something that checked for equality. Okay, because if I want to do the jump, if I want to implement the jump instruction, right, when does a jump take place? You compare 2 registers, register something against register 0, right? And those 2 things are either equal in contents or not. The jump occurs if they are equal in contents, okay? But how do you tell if 2 numbers are equal? Okay, it almost is a stupid question when I say it, right? Because you just say, well, derp, Dr. McKinney, you just look at them and they're either equal or they're not. Okay, so, but let's back up a minute and think about this properly. How many different, if I've got 2 bits, how many different combinations do I have to consider? 4, okay? All right, so 0, 0, 0, 1, 1, 0, and 1, 1, okay? All right, so those are my 2 input bits. And I want to output whether or not they're equal. All right, so is 0 equal to 0? So this I would want a 1. What would I want for these 2? What would I want for this one? Okay. All right, so they're equal whenever both bits are the same, right? I mean, duh. Okay, but the better question is what truth table are we staring at here? Okay, how many different basic circuit elements did we talk about way back in the day? There were 7, okay? What were they? The NOT gate, AND, OR, NAND, NOR, XOR and in XOR. Guess which gate this is? This is in XOR, which we've never used up until now, right? That's the gate that does equality checking, okay? Now, let's think about why it's in XOR. Okay, if this were regular XOR, what's 0 XOR 0? 0, okay. What's 0 XOR 1? Okay, 1, and then, well, notice that what we have for XOR is exactly opposite of what we have for the equality. So if this is XOR, what's the equality? In XOR. That's how I know that's the right one, because it's opposite of XOR. Yeah? Well, finally, we have a use for poor old in XOR. Okay? All right. So if that's how we check if a single bit is equal to a different single bit, how would we check if 8 bits are equal to 8 bits? What do you think? Yeah, use multiple in XORs. So if I use 8 of those things, that will tell me if each of the bits are equal to each of the bits, but then when are the two numbers equal? Only when all 8 of those in XORs are ones. Okay, so I've got, imagine I have 8 in XOR gates. I'm only going to be equal if all 8 of them have the same output. Okay, all a 1. What is that code for? All right, so let me start clicking up here. Okay, so, all right, you'll notice that the in XOR is so rarely used that it's not even up there in our palette, but that's okay. It's here in the gates tab. So let's do in XOR. Okay, so how many of these did I say I needed? 8. Okay, and you guys will humor me and pretend that they're all wired up to the inputs correctly. All right, how many is that? 5, 6, 7, and 8. Okay. All right, now we're obviously not finished, right? Let me zoom out slightly. There we go. Okay. There's all 8 of them. Each one of these in XOR gates outputs a single bit. And the two numbers are only equal if all 8 of those bits are ones. Okay, so what is that code for when I say all of them have to be ones? Which gate? You know, which gate is code for if they all have to be equal to a 1 and. Okay, but this is a little bit different from and as we've seen it before, because up until now, how many inputs has and had? Only 2. But here, I almost want 8 of them. Okay, so there's 2 ways that we could do this. One would be if I take 2 bits and I AND them, and I take the next 2 bits and AND those, and I just treat it pairwise, could I do this with a cascade of 7 AND gates? 4, then 2, then 1? Would that make sense? Right, so what I could do is say, all right, take the output from the first two XOR gates and AND them. That gets me a single output. And that would be 1 if the first two were equal. Then I could do the second two, the third two, and the fourth two. And then I could take the first and the second pair, the third and the fourth pair, and AND those, and say, are the first four the same? Are the last four the same? And then I could take those guys and AND them and say, okay, were the first and the last four the same? If yes, then all of them are the same. Done. So I would have 4 ANDs, 2 ANDs, 1 AND. Could I theoretically do that? Okay, but there's a better way. It is possible, through the miracles of silicon gate fabrication, to make multi-input AND gates. Okay, so this is like a regular AND gate, except it has 8 inputs instead of 1. Okay, so isn't that a lot cleaner in spirit, right? And it is possible to fabricate these things so that you don't have to think of it as a series of AND gates, kind of one after the other, okay? So all I would need to do is wire each of the XOR outputs to one of the inputs of the AND gate. There are 8 of them here. And then there we go. We've got an equality checker. Okay, so does that kind of make sense? Yeah? Okay. Well, what other things do we need? We need rotators. Obviously, I didn't build the XOR gates or anything like that. The AND, the OR, and the XOR are just 8 of them in a row. That's really all you do. It's nothing, not rocket science. Okay. But so what I want to sort of start to talk about now is how do you actually know which instruction you're executing? Okay, so with the Brookshire, the machine code commands, right, every command took 4 hex letters to represent, right? So for example, if I had the instruction 20FF, okay, what does that instruction do? Loads register 0 with the bit pattern FF, okay? As opposed to, of course, 10FF, which does what? Yeah, with whatever the contents of memory cell FF were. So it would go out, find memory cell FF, say what's inside there, grab it, and then throw it in register 0. Okay, whereas the first one takes the actual number FF and puts that in register 0. It has nothing to do with memory. Okay, all right, so how do we know that those two operations are different? Like for you guys staring at this on the board, how do you know that these are two different operations? Because what's always this part of an instruction? What did we call that first character? This is called the opcode, right? And that told us which kind of operation we were doing, okay? And if I've got a single hex character to represent that, there are theoretically 16 of them, right? 0 through F. Now, in our architecture, we don't use all 16. We only use 12 of the 16, 1 through C. Okay? Does that make sense? Okay, so what I want to do then is sort of say, well, if I just look at this instruction, I can tell that the number 2 and the number 1 are different things because I'm not a bonehead. Okay, but how would a computer sort of decode and know which operation you're doing? Okay, all right, so let me make a new circuit. Okay, so there is, all right, so what I'm going to do is I'm going to take a 4-bit input, okay, and I'm going to display it in hex, right? It's still 4 bits. I'm just displaying it in hex, okay? And then what I'm going to do is I'm going to make a 4 select bits, okay? And I'll explain what I'm doing here in just a second. Oops, that was the wrong one. Okay, so what I want to do is, let me put a couple of lights out here. And now imagine that I've got 16 of these things, just for sake of demonstration. Okay, and I'm going to put the first one connected to there, and the second one connected to there, and so on. So imagine that there are 16 of these things in a row, okay? So let me actually make a few more. Okay, so what a decoder does is, so how many different patterns are there for my input if it's a 4-bit thing? 16, right? 2 to the 4th. Okay, so if I have 4 bits that tell me which operation I'm doing, then there are 16 possible combinations of those 4 bits. And what a decoder does is it outputs a single bit. There are 16 different possibilities, and it tells me which of the 16 possibilities I have. Okay, so if my input is all zeros, I get the top output on. If I change the input to a 1, right, this is hex 1, not binary 1, then that says the second output's on, going to be on, and then the third output and the fourth output, and so on. Okay, so what about if I change this? Oops, I don't want to mess the label. Okay. Okay, so let's say I make it a 1. Which of the outputs is on? The second one, okay, or I'll call this the 1 output, right? And if I change this input to a 2, which light turns on? The next one, okay? And that means that this unit gives me a way to know which of those 2 operations I'm doing. And so I could say, okay, if this bit is a 1, that tells me that I'm doing this kind of operation and configure all the rest of the bits of the processor to work accordingly. And if the next one is, then I have to reconfigure everything to do something else, okay? So these outputs, there would be 16 of them, although we only actually would use 12 for the Berkshire architecture, would allow me to then control which parts of my computer are active and when, okay? Does that kind of make sense? All right, now the when part is a little bit harder, okay, because that requires a notion of time. Do I have a clock on this thing? Not yet. Okay, so we'll introduce, and next time, right, what we'll add in here is the idea of a clock. We'll talk a little bit about how we would do data storage, that sort of thing. But again, we're sort of looking at each individual piece, and if we start putting all these together, it's like we could literally design an entire processor. Okay, all right, so couple quick pieces of business. I'll have your exams back for Friday for those of you who I owe them to. When, of course, is our final? Next week on Friday at what time? 9 to noon. No, because grades are due that following Monday at 4 o'clock. And, well, Miriam Foster isn't here anymore. None of you guys know Miriam. But Julia Perry in the registrar's office is also not somebody to be messed with. So yeah. Anyway, um, right. And stay tuned on Canvas for, I might drop a few hints as to what you should expect on the final. Like maybe I'll drop a effing study guide, right? Something like that. Or maybe I'll drop my new sick mixtape, Cody. All right. See you guys Friday.